Thank you very much, Shahid, for asking me to talk and to look after this session. And it's really nice that we managed to stay in touch. And maybe this will be the beginning of something more.
Yes, yes.
I may or may not have understood my mandate very well. I'm going to have some amount of reference to the material presented by others in this session, some overview, and some of our own work. It's some sort of
Yes.
combination of these things. Since you've
Yeah.
given me 50 minutes altogether, there's enough room, I think, time for.
Yeah, you can. You have a lot
But
of.
anyway, it's very kind of you to ask me to talk, and let's see how this goes. And it's also a nice opportunity to get to know people that I've not met before, including the speakers.
Yeah, exactly. That you kind of there's a community in Pakistan that you'll get to know, which I think would be one sort of plus for both of us.
So let me just start sharing. So you can see my opening slide, I trust. Yeah. Okay, so this session is called Active Matter Self-Organization. That is the title that Shahid handed me. So as I said, it'll be a patchwork of my saying a few words about what people are going to say, a fair number of words about the subject as a whole, and then about a moderate amount about the work we have done. So let me, my talk is really an overview and recent results on active matter, and I've just tried to illustrate on this kind of montage slide active matter in many regimes, fish schools, bird flocks, active flows inside one cell. What you're seeing here is the nucleus of a cell going round and round because of flows on an intracellular scale. These are artificial systems that I'll say a little bit about, systems that convert vibrational energy into walking. Just a second. And these are bird flocks that I'm very fond of that we saw in the sky over the old building that TIFR had in Hyderabad before it moved. So this is a student of mine took this video, and we really view all of these systems kind of in the same way, saying, look, they are self-driven, they take up energy, they move, they interact, they organize. And so we'd like one big framework to understand all of these systems. And among the things you'll realize from seeing these movies is that they're also very beautiful. So a lot of our motivation in studying these systems is just that, my God, how lovely this is, what's going on. And knowing what's going on doesn't make them less beautiful, it makes them more beautiful. I'm supported by funds from the Science and Engineering Research Board India, and until recently by a grant by a chair from the Tata Trust. I'm at the Institute of Science. Okay, so now let's first talk about this session before we go any further. Aside from my presentation, there are 3 talks in this session by Ammar Ahmad Khan on using self-assembled soft structures, liquid crystals, to create materials with anisotropic conductivity and with potential applications in photovoltaics, optoelectronics in general. So Ammar will tell us about that. On a fairly different track is a talk by Sabi Anwar, who will talk about birds and how they navigate, and the magnetic aspect of that navigation, in which, according to his rendition, quantum mechanics plays an essential role. A third talk, which is somewhat more situated within the kind of active matter that I'm familiar with, is by Junhua Huan from University of Science and Technology, China in Hefei, where he'll explain how bacterial swarms can carry out chemotaxis, even though you would think the conditions aren't actually propitious. And there is a kind of thematic unity to this session, because you will see that active matter in different ways involves things like flocking, things like collective motion on a more small microorganism scale, and a great deal of liquid crystal physics. So in that sense, even though these talks seem like they're from all over the place, they do belong, and the kind of stuff I talk about does belong in one session. So I think it's not a bad way to organize a session. In slightly more detail, Ammar Ahmad Khan will talk about the supramolecular self-assembly of disc-shaped molecules into strongly anisotropic structures, including thermally reversible gels, whose properties you can control, and applications thereof. The other part of what he'll talk about is actually closely related to topics that people in kind of mainstream active matter are interested in, which is using liquid crystalline pattern substrates to create and anchoring to create topological defects in nematic liquid crystals, which you have as a kind of overlay on those. And it's known that in assemblies, strongly packed assemblies, confluent assemblies of living cells, they have their motility and their tendency to form mounds and so forth is strongly linked to a certain class of topological defects called +1/2, which I may say something about. So Ammar's talk has references to both these aspects, so I thought I'd mention them. Mohammad Sabi Anwar will present you tutorial talks on how migratory birds find their way and find their way to the right destination. They do this by exploiting photosensitive reactions whose yields depend on the local orientation of the magnetic field. So you can imagine how they might be able to use this to navigate. And you can imagine, given that you're talking about chemical reactions with a magnetic field dependent yield, how quantum magnetism and quantum chemistry might be important. And he will tell us about that. Junhua Huan will talk about the following interesting question, which is that many of you will have heard about the phenomenon of chemotaxis, where a bacterium manages on average to steer up a nutrient gradient by doing the following. As long as it keeps measuring the amount of nutrient, and as long as the amount of nutrient seems to be increasing, it keeps going in the same direction. If it finds that it's not increasing, it does something to its flagella that make it randomly change direction. They unbundle, they randomly change direction. And then it sets off in another direction. The average effect of this is that the bacterium finally ends up displacing itself up a gradient. So if it thinks life is getting no worse, it keeps going. And if it finds life is getting worse, it randomizes. And the average effect of this is climbing a gradient. The only thing is, this is fine if you're one bacterium, if you're very few bacteria. If you're many, you might think it's difficult to turn around randomly. Other things come in your way. And the question is, in a concentrated swarm, how is this phenomenon known as a chemotaxis? How is it implemented? And what Juan Junhua will show us is that clustering and alignment, even though an individual's gradient response can be small in this dense situation, their tendency to come together and to align can amplify this weak individual gradient response and give you effective chemotaxis, enhanced chemotaxis in a swarm. So these are the three talks that will follow mine in this session. I don't know what the policy is regarding questions, if they're to be asked only at the end or if people want to interrupt in the middle. I will leave this to Shahid to decide. You can choose.
Yeah, so I think how we'll proceed, Sriram, is that people, if they have questions, should enter them in the chat box. And if it's an urgent question, they can raise their hand. And I would then, depending on what stage you are in your talk, I could then interrupt you or not.
Okay.
So just leave that to me, and you just get on with your.
Okay. Great.
Yeah.
All right. Okay. So let me now come to my talk proper. I'm going to give you an overview of what we call active matter. I'll give you not only a motivation and early results, but some very interesting prehistory of the subject. Then I'll talk about just a couple of topics from our work. One is the instability of liquid crystals made of living things and how you can escape that instability. Interestingly, you go from a state that is turbulent when it's slow to a state that's aligned when it's fast, which is quite the opposite of fluid turbulence. I will not tell you about defect unbinding in active matter. That's a whole other talk, really. Then I'll tell you about another fun story which you recently got interested in, which is the non-reciprocality or non-mutuality of interactions. What that means and what it implies, I will come to in the talk, and then I'll summarize. Okay, so let me begin with motivation and so forth. So we will all agree, and Shahid very eloquently explained this during his overview in the morning about how the living state is not thermal equilibrium. The living state is a driven state. And, you know, if you're well away from birth or death, the living state can be treated as kind of a stationary driven state. And it's different from conventional, from more kind of prosaic driven states. Like supposing you have a wire and you have the two ends are connected to the terminals of a battery. Then the interior of the wire is driven because of energy input from the tips of the wire. But in living matter, as Leibniz remarked, living matter is made of stuff, each of whose components is also living. So living matter is a macroscopic, out of equilibrium thing made of units, let's say cells, which are themselves out of equilibrium. So in a treatise called Monadology, the philosopher Leibniz, not just philosopher, mathematician, many things, said that a living thing is a machine to the least of its parts, a machine made up of machines. This is amplified in a very nice way in a review article by Dan Needleman and Zvonimir Dogic a few years ago. And this general point about the living state being not thermal equilibrium is rather nicely restated by Rob Phillips in a review article in the Annual Review of Condensed Matter Physics a few years ago called Napoleon is in Equilibrium. So what Rob means is Napoleon is in equilibrium because Napoleon is dead. Okay? And another feature about this idea of a machine to the least of its parts that you will see during this talk is there's a similarity from one scale to another scale to another scale to an amazing degree. What goes on inside one cell because of filaments and motors, or what goes on inside tissue because of cells as the elements, or what goes on in a group of organisms because of the individual organisms as the element, is very similar. It's described by really the same equations in many ways. And of course, before I go any further, I should commend to you some of the classics of the literature. One that Shahid mentioned is the monograph called What is Life by Schrödinger. And one is the beautiful book by Darcy Wentworth Thompson, which recently celebrated its centennial, on growth and form, on how physical laws shape what living things look like and how they move and so forth. And many of the ideas that we talk about today are just echoes and working out of ideas that were adumbrated very long ago. And active matter is the condensed matter physicist's view of the living state. That's a fair way of describing it. Condensed matter thinks that any collection of anything is condensed matter, whether it's molecules in a gas or liquid or solid, or galaxies in a cluster, or organisms in a flock. And this way of doing the physics of living things has, in a sense, you can say, it's sort of gone viral. And part of my effort in this talk is to explain why. Of course, gone viral is a bad term to use in this context because a virus on its own isn't really alive, but that's why I put it in as a kind of joke. Anyway, living examples are always nice to look at. You can think of living matter in many, many different settings. You can take a flock of living creatures. These are millipedes on the University of Hyderabad campus, captured on film, on video by my friend Surjit Dhara, who works on liquid crystals and therefore was very excited by this system. You can imagine a thin, one cell thick layer, of confluent layer of cells, an epithelial tissue. This is here in a group from Paris, I think, from Curie Institute. You can take stuff out of one cell. You can take biopolymers like here, I think it's probably actin, motors like myosin, and the chemical fuel needed to run them, and look at them in vitro, and they form spectacular, very dynamic, very organized patterns. Here from a group at Senussi et al. At University of Paris. But there are some utterly unexpected systems which are also in principle described by active matter, including systems you'd never guess at. Like imagine taking a two-dimensional electron gas and imagine pumping it with microwave radiation. Now that two-dimensional system is receiving energy from a third direction, and it's carrying out all kinds of movements, and it enters these interesting states called zero resistance states. And these are states in which currents spontaneously set in. Hello, is someone not muted? There's some interruption coming in.
Okay, yeah, no, everybody should mute, please.
Yeah. Um, Anyway, so this you can even make artificial quantum active matter in radiated 2 DEGs, and this has been analyzed in that framework by Alicia et al. You can make artificial self-propelled objects either by having objects of a non-trivial shape and actuating them magnetically, like in this work by Ambarish Ghosh from our institute, or you can take a surface, you can put a particle on it, as in this picture. This is a top view. You can vibrate the surface up and down so you don't pick a direction in the plane, and this particle starts walking. I'll say more about this system. We have some nice experiments and some theoretical analysis of these systems. This was the PhD work of Nitin Kumar, a joint student of Ajay Sood and me, then at IISc, now a professor at IIT Bombay. And I'll say more about this. One other kind of fun system is to take a dimeric elastic object like this, and supposing the two heads are different in some way. For example, supposing one of them has a different damping response when the dimer is stretched from if it is compressed. This is work done by Vijay Kumar, now at ICTS Bangalore, and he showed that a system like this, if fed with noise of a non-equilibrium character, will start walking in one direction, slightly noisily. So it's a funny kind of Brownian ratchet in which the ratchet structure comes from the internal structure of the object and not from the terrain on which it's walking. So this is a simulation, and we've been hoping that someone will recreate an experiment, but not seen it yet. Anyway, that's lots of examples just to show you these kinds of ideas are all over the place. Why should we care about this? I think the major reason we should care is that living matter is one more kind of matter, and we'd like to understand it. After all, biology happens because of physics. It doesn't happen by defying the laws of physics or violating the laws of physics. So can we understand the laws of living matter? Can we understand life from subcellular all the way to groups? Can we understand it in sickness and in health? One interesting point I want to make at this early stage is that, as many very learned people have remarked, physics enters biology in two seemingly different ways. One is in the form of information processing. After all, a very important part of life is that organisms make copies of themselves. Not only that, organisms go on building the objects that are needed to keep themselves functioning. They go on synthesizing proteins through a elaborate mechanism, and that mechanism is not an arbitrary mechanism. It's a faithful mechanism. It reads and implements instructions very carefully and precisely. And so information processing on every time scale, from seconds to millions of years, from time scales in the running of a given organism to the birth of a new organism, in the life of an organism as it senses its environment and turns around, out to scales on which organisms change because of evolution. Information is very important, and there's lots of statistical physics in that information processing. The other place in which physics enters biology, of course, is mechanics and non-equilibrium energy conversion and metabolism. And the success of the active matter enterprise has been to say, for the time being, we'll focus on mechanics rather than worry about information. And so, as you will see in my talk, I'll really talk about the mechanics aspect only. But eventually, the hope is that one puts in more and more functionality into the ingredients of active matter, including information processing, and see how they sense, how they signal, how they make copies of themselves, how they evolve. But we are not there yet. So I'll tell you about the mechanics part of the story. Okay, so active matter, therefore, consists of active particles. Active particles, which living systems or their components or artificial realizations, are objects at whose scale detailed balance, which you must know from physical chemistry or stat mech, is broken. That is to say, they are supplied with a they're provided with a sustained supply of free energy, which they transduce into movement. Okay, and this is kept up, and therefore the components of active matter are perpetually out of equilibrium. collections of these kinds of components are called active matter. So the physics of active matter is the physics of systems made of components with broken time reversal, dissipatively broken time reversal invariant. These brief references down here are about how you use this idea to build the equations of active matter. But you can read about them. This talk is not the place for it. And as in any condensed matter system, we're interested in the sort of structural aspects of the components of the system, the constituents of the system, and the structural characteristics of the phases they form, and the characteristic defects that form in those different phases. So you can imagine particles with no particular structure, but which at a given moment do some energy dissipation because of chemistry at some random point on their surface and start moving around. So these are chemically propelled drops. You can think of them as kind of scalar active matter. They may transiently have some particular point where the reaction takes place, so they have some direction. But on the whole, they're kind of round particles jostling each other and running around, doing something very different from Brownian motion. You mustn't forget that. And Shashi Thuttupalli has beautiful particles of that type at NCBS, chemically propelled droplets. You can have particles which are anisotropic, like this rod, but which are the same on two ends. So then they'll form traditional liquid crystals. They form pneumatic liquid crystals. Even particles whose head and tail are different could end up packing in a way that respects the axis but not the head and tail. So these two are both classic pneumatic liquid crystals. You can also imagine particles which have a structural or dynamical polarity packing to form an assembly which also has a macroscopic polarity. Now, one very interesting point which should be exciting to people who know about liquid crystals is that until recently, people would always say that, in physical liquid crystals, you get this kind of packing or this kind of packing. You never get a macroscopic vectorial polarity. You don't get a polar pneumatic. But Noel Clarke's group, I think just last year, has found a relatively simple system in which there is a real pakka macroscopically polar pneumatic. This is amazing news for a field that has been around for so long. Nobody has made those systems active yet to see if they form flocks. But it's really cool that Noel Clarke, at this stage of career, is still turning up spectacular new results that turn the game on its head once again. Now, if you had a simply pneumatic system, this type of system, then the topological defects are what is called strength half. If you go around a defect, your orientation rotates by 180 degrees. It can either rotate by plus 180 or minus 180. And these are beautiful defects in active pneumatics. From a nice review article that I would recommend to you from the group of Julia Yeomans by Amin Dost Mohammadi and others that came out a few years ago. For a very detailed understanding of the state of the field a few years ago, I would, even though it's an article on which I am one of the authors, I would still recommend this article in Review of Modern Physics from a few years ago. Okay, I'm going a little slowly, but maybe it doesn't matter. It's more important to uncover a little than to cover a lot. So now when we write down dynamical models, it's important to ask what dynamical domain we're in. Whether the dynamics of the system is in an ambient fluid medium, or it's a collection of things that are motile but on a kind of inert momentum sink. Because clearly here, when one of these sheep speeds up or slows down, it's true it exchanges momentum with the Earth, but it exchanges it on a scale that's like in the Musbauer effect, where you emit radiation, but the whole sample shifts. So that hydrodynamic interaction you can just forget, because it's averaged over the whole system. The hydrodynamic interaction in a fluid medium is dramatically important, and we'll see a little bit about that during the talk. Now, again, I'm still in the background part of the talk, and I think that's really the most important part of the talk. I was amazed about 10 years ago when I was looking through the literature for something on what is called the Curie principle, which is a principle relating a structural symmetry to the permissible currents in some system. Looking for that article, I found that one of the articles that refers to it is this absolutely prescient article by two very distinguished chemical engineers and fluid mechanicians from 1969. They talk about many of the same ideas that we thought we invented in 2002. They talk about an active stress. They talk about, these words are all direct quotes from their article. They talk about motion without the intervention of outside forces. They say that such engines operate in living systems. They say, come on, folks, let's work on this. They say this is virgin territory for research in complex fluids. They say that a microscopic understanding of these systems will need a statistical mechanics not yet detectable on the horizon. They advocate the creation of polymeric, they advocate or predict that at some point it will be possible to make polymeric or colloidal systems approximating living protoplasm. So they're telling you, look, guys, let's make artificial active matter from complex fluids with some clever chemistry. They talk about, one thing is curious, they're not that interested in these uniaxial contraction, which is characteristic of muscle and characteristic of actomyosin systems. They say, yeah, we know about that, but we are interested in another kind of activity for some reason. They make their active stresses by objects bilinear in gradients of temperature, gradients of concentration, etc. In some sense, therefore, they were looking at scalar active matter and its active stresses. All of this before any of us had done anything on this subject. And amazingly, also, the other people in the field didn't hear about it. I stumbled on this article, which is, given its beauty and its importance, I think is, even to date, is only referred to by about 40 people in the literature. And yet, the important question from the point of view of historian of science is, why did this paper not launch a field called active matter? And I thought about it a little bit, and I comment on this in an article I wrote in a special issue of Nature Reviews Physics, probably the first volume, or maybe not, first year of it anyway, in a special issue commemorating 200 years of the amazing fluid mechanician, mathematician, physicist, etc., George Gabriel Stokes. Stokes of the Stokes theorem, Stokes of Stokes flow, Stokes of Stokes and anti-Stokes, same guy. Okay. So I wrote an little article called Active Fluids. And I think the reason that this great paper didn't launch active matter is the ground had not been prepared. Nobody yet knew how to write down hydrodynamic descriptions for things other than fluids. People knew how to write down hydrodynamics of fluids. I guess people knew how to write down elastodynamics for solids in some sense. But they didn't realize there's a whole continuum of things you can do in between. They didn't realize that any complex fluid, any broken symmetry system, any liquid crystal has its hydrodynamics and the same organizing principles, but including this notion of spontaneously broken symmetry. If you fold that in, you can write down hydrodynamics of all these systems. Nobody knew that phase transitions in fluid and magnetic systems could again be described by coarse-grained hydrodynamic descriptions. The kinetics of phase transition could be described that way. None of this formalism existed. Martin, Parodi, and Prashant hadn't written their great article in just a few years later, 1972. Hohenberg and Halperin hadn't written their review on dynamic critical phenomena, 1977. Just a few years. But the funny thing is, if you're too early, sometimes it's not that people, after the formalism has been developed, go back and discover that paper. Sometimes it takes 50 years. So somehow this is very much in my mind a kind of amazing fact about science, how these things work sometimes. Anyway, still on background and rapidly running out of time, I should talk till about 2:10, 2:20. No, sorry, I'm sorry, I'm doing my time. 1:50 or thereabouts?
Yeah, you have time.
Yeah. Okay. All right. So now let's come to models, and let's come to actually, now we'll start talking a little bit about the kind of work we do. We were motivated by flocking models. Flocking was a purely descriptive theory rather than a mechanical theory. The theories of flocking, initially invented, I think, the motivation was partly to understand animal groups and partly to make convincing movies of stampedes. I think that's what Craig Reynolds, a computer graphics expert, was doing. And he wrote down a model. He said, if you take a bunch of objects which have a front end and a back end, and they like to move forward, and you make a rule that they don't get too close to each other, they don't bump into each other, they don't go too far away from each other, they like to be somewhere near each other, and they like to go the same way as their neighbors. And supposing you say that they do this with kind of finite accuracy. So then there are two control parameters: how dense the system is and how accurate is your estimate of your neighbor's orientation. Density and noise, like density and temperature, kind of. And these guys found that these systems, if the density was high and the noise was low, spontaneously formed a flock. Flock meaning a group of things moving on average in the same direction. You could assign an order parameter to it, which is the sum of the, which is take the unit vector assigned to each particle, add them all up and divide by the number, time average a little bit if you like. And you will find that at high density and low noise, that quantity is non-zero in magnitude. At low density and high noise, it's zero. And those were flocking models. And before I go on to the work we do, let me tell you about the connection to Shahid from this work, which is that some years ago, again, at this point, 10 years ago, we realized that people had been studying this phenomenon, two groups, Andreas Bausch, but Shahid and others, including Justin Malloy at UCL or Imperial and UCL, is it? Yeah. I forget the place.
Yeah, Justin was at National Institute for Medical Research at that time.
Okay, right.
And this was my first paper from LUMS, and with a very dear colleague, Sohaib Khan, who was in computer science. So this was, in terms of LUMS history, this was also one of the first papers from the School of Science and Engineering, and one of the first collaborations between, a computer scientist and in my case, a biologist.
Right. So what they found in this paper was that at low concentrations, so by the way, the system is actin filaments, myosin motors, and the chemical fuel for the motors, namely ATP. And other things, I'm sure there's lots of magic in these things. But anyway, essentially, what they find is that low concentration of, I guess in this case, filaments, or is it myosin? Mix per mil, myosin, I guess, right? Or ATP.
That's right. That's myosin, and the concentration is for myosin filaments.
And what do you find at low concentration? Random. Higher concentration, you start to move coherently, and very high concentrations, you form order. And this is the orientational distribution, which is broad and consistent with isotropic, and it goes to dead perfectly oriented. So this is a flocking transition in active filaments. And so that, this work actually was one of the ways in which Shahid and I learned about each other in some sense. And so it's nice that, it comes in very naturally in this talk, and it forms a natural connection to this gathering and this community. You can do similar things on other cells. You can, of course, do similar things on computer models. That's what VTech and company did. Toner and Tu then made a field theory of it and showed that it manages to be truly long-range ordered, even in 2 dimensions. A group in Budapest showed that you can find the same phase transition in keratocytes, cells extracted from fish scales. All of this, and now is where I come to the work that we did. So what struck us is that all the theoretical models that people have been discussing up to that point on flocking, as I said, were descriptive models. That is to say, you have an object, it has its neighbors, and it has a rule. And that rule is that it tries to point parallel to its neighbors. But the mechanics of how that can happen was not taken into account. If something is pointing in a certain direction and moving in that direction, then if it changes its direction, that means it's changed its momentum. If it has changed its momentum, since there are no external forces on it, it has to do so by sharing that momentum in some way with its surroundings. So if somebody swimming like this suddenly changes direction like that, it's because they push the fluid in some way. That pushing of the fluid pushes others. So the hydrodynamic interaction that is a necessary accompaniment to changes in momentum is sort of ignored in simple flocking models. And flocks in fluid, we discovered, are radically different. Momentum conservation changes everything. So what we did was really just to say that if you've got motile organisms, with some interaction that makes them tend to want to align with each other. So if you've got a system of, bacteria moving around in a fluid, excuse me, then what are the correct equations to write down to describe this system? So we asked a totally general question. What, in the same spirit as the hydrodynamics of ordinary liquid crystals, which we've known how to write down for 50 years, what is the hydrodynamics of living liquid crystals? And living means each particle has some motility apparatus which interacts with the surrounding fluid in such a way as to make it swim. So my then student Aditya Simha, now regret sadly no more, and I wrote down the equations of active liquid crystal hydrodynamics. Active because each particle is endowed with self-propelling stresses. And we wrote this down in complete innocence of cytoskeletons and actin filaments and all that. We were thinking of organisms in a fluid, big scales like fish, or maybe small scales like bacteria. And the reason I'm stressing this is a vindication for just blue sky research. You think about a general question. If you have a system with a tendency to align and a tendency to move in a fluid medium, what is the inevitable form of the equations of motion for that system, just on symmetry grounds, okay? And we wrote this, and the same equations surfaced 2 years later in work from the Curie Institute and ESBCI and Dresden in the form of the active gel theory of the cytoskeleton. Okay, so I should also emphasize, it's probably the right point to emphasize, that you can see that this is not traditional biophysics. Traditional biophysics has a good deal of biological realism in it, often. A lot of it actually is using the experimental tools of physics to do biology. A lot of it engages more with the, with the chemistry of the system. But you can do this kind of step back and take a big picture approach. And many people nowadays call this biological physics, because biophysics at institutes like ours, for instance, is a name already taken by the structural biologists. People who do X-ray or NMR to figure out biomolecular structure are called biophysicists. So just to distinguish us and them, I'm afraid we call ourselves biological physicists. But actually in Europe, and especially in Germany, for instance, that distinction is not made. People doing our kind of stuff are also called biophysicists. Just sociology for you. Anyway, so what did we do? I will not bore you with too many equations. We wrote down equations for the orientation field and the hydrodynamic velocity field of a system of swimmers. We said that spatial variation in the orientation causes flow. Flow acts back on the orientation and changes it. Apart from that, you have some forces which make the things try to align. And you ask, you put all this in and do a little bit of fairly elementary maths. What happens? We did this at that stage, both with and without fluid inertia. But the most important results at that stage of the game were the ones where you ignored inertia. So you said that assume that things are viscous enough and moving slowly enough that whatever happens at one location reaches everywhere else instantaneously. This will not be true on very big length scales, but on those very big length scales, the velocity fields themselves have decayed a lot. This is zero inertia hydrodynamics. This is the hydrodynamics that Stokes, again, liked to work in. Okay, so what we predicted, among other things, so first of all, in order to predict, we had to build the equations. We built the equations by saying that the atoms or the elementary particles of living liquid crystal hydrodynamics are swimmers of this sort, and each of them is a little dipole of force. Either it pulls fluid in along its axis, like this alga, or it pushes fluid out along its axis, like this bacterium. And if you put these together, you can build these equations by assembling these. We built them directly by pure thought and post facto justified it by these microscopic pictures. And what we showed was that if you took those equations and created an aligned state and perturbed that aligned state, then you found that if there were swimmers of this type, then that aligned state inevitably and unavoidably in the zero inertia regime always goes unstable to perturbations of a splay type. There's a parameter sigma A, which is the the density of these force dipoles. We call it the active stress. Negative sign of that has to do with this type of swimmer. A positive sign has to do with this type of swimmer. These guys are always unstable in space play. These guys are always unstable in bend. The presence of a single scale of stress in a system with a viscosity mu introduces a single time scale. And what we predict over the regime in which Stokes hydrodynamics applies is that no matter what length scale of perturbation, its growth rate is independent of that length scale. There is a single time scale of growth rate, which is given by viscosity divided by active stress. So this has many other consequences. And there have been nice experiments that confirm this in detail from the group at Barcelona, Francesc Sagues's group, and experiments also by Shivashankar, on which we did some theory, which showed the same phenomenon taking place not in an extract, but inside one cell. Take one fibroblast, place it on a fixed circular geometry big enough to accommodate it. It spreads and becomes a large circular cell with a nucleus inside, of course. And what happens is that this alignment and slight tilt of filaments takes place in the region around the nucleus. It gives rise to these kinds of flows, and those flows rotate the nucleus. We can actually calculate the velocity profile as a function of distance from the center, from the nucleus, and we can measure it, or Shivashankar and group measured it, and it agrees remarkably well. Even the magnitudes, rotation rate of a few degrees a minute, agree very well with with our estimates of active stress and viscosity. But these studies by Sagues and company show the bend instability that we predicted for extensile filaments, how that instability, when taken well beyond the linear regime, finally releases topological defects that completely destroy the structure. All of that is beautifully shown in this study by Francesc Sagues. Okay, so I'm almost done with my time.
You have 3 minutes more, so yeah, I mean.
Okay. So let me skip ahead to the artificial systems. Okay, I'll skip the active turbulence work. Where is it gone? Let me skip to a very different part of the story, and I'll close with that. It's getting stuck. Just a second.
Yeah, you started 3 minutes late, Sriram, so you actually have five minutes, a bit more than 5 minutes.
That's good, but I should also leave a little time for questions. So
sure.
I'll
yeah.
So what I'll do is I'll talk about non-mutuality. So now a seemingly completely different part of the story, okay, which will involve self-propelled objects in an elastic medium. You know, when you have interactions between two particles based on a potential energy of interaction, then the potential energy is a function of the separation between these two particles, and the force on this guy due to this and the force on this guy due to this are equal in magnitude and opposite in direction. Newton's third law. Okay? But if you have interactions that don't depend on an energy function, but depend on some kind of taxis, this guy is moving like this guy senses some chemical and it turns. And if these two guys are different, those interactions are not at all governed by energy functional, and they can be very, very non-symmetrical. Locusts, the flocking interaction between locusts is because the locust behind is trying to eat the locust in front, and the locust in front is trying to run away from the locust behind. This idea finds echoes in many places. In ordinary life, A can like B and B can hate A, right? So it turns out there's a gorgeous realization of this in motile particles in an elastic medium. The subject of non-reciprocal or non-mutual interactions is much studied these days. There are references on here and work by Saha Golestani and others, Cristina Marchetti's group, Michel Fruchat and company from Vincenzo Vitelli's group. But I'll just tell you a little bit about what we've done. I spent a long time on background, but I think that's okay. You can read about my work elsewhere. So we looked at, basically, we took off from Nitin Kumar's work on flux in a granular fluid, in which he showed that if you have a vibrated layer, which I said can make particles walk if they're elongated and pointed, and if you disperse those particles among a bunch of other round particles, remember just one layer, particles are about 1 millimeter in diameter. This is macro physics. If the density of those beads is not high enough, nothing much happens. If you just increase the density of those beads a bit, then they communicate the movement of the rods in such a way that the rods end up aligning with each other and forming a flock. And you get this fabulous flocking transition as a function of bead concentration, rather like the flocking transition in Shahid's experiment as a function of actomyosin concentration. Now, supposing you make the bead layer so concentrated that it's no longer a fluid. Supposing it's a monolayer, a vibrated monolayer of beads which are a crystalline pack. Then what you can see from this, these are simulation images, but they're mechanically faithful simulations. So they're like experiments. In the fluid, when the rod moves, it drags the beads. We've labeled a few of the beads. In the crystal, when the rod moves, it goes along and those beads stay behind. Question then is, do the rods still talk to each other through the medium? And the answer is, it looks like they do. You can measure the strain field in the ambient medium and you find it's non-zero. So we wrote down a theory of this system saying that each rod moves in a direction dictated by which way it's pointing. The presence of a moving rod in the bead medium produces a local force, a local point force in the bead medium. Strains in the bead medium reorient the rod. And you put this together, what you find first is one moving rod, if you co-move with the rod, produces a displacement field which has a very interesting analytical form which you can check in experiment. This came from our simple analytical theory, doing integrals that you can look up in integral tables. Okay? And what you find is that when a rod is moving like this, the medium in front of it hardly senses that it is coming. The distortions are highly screened in front. Behind it, the distortions are not screened. This mathematical form, highly screened in front, unscreened behind, has an amazing consequence. First of all, it's a prediction of our theory. You can measure it in the experiments or in the particulate simulations, which are like experiments. We predicted that it decays as x to the minus half behind and exponentially in front. So we took the measured displacement field and multiplied it by x to the half, and you find that behind it's dead flat, which means it was x to the minus half, and in front it's highly screened. We then take this and put two particles together and ask what happens. We check this in the experiments I told you about, vibrated layer. This is the motile particle. As I said, this creates particles that walk. And the particles walk because when you toss it and come down, if one end is different from the other, it lands on that end and starts walking. And we measured what the particles do. What happens if you put two particles? The particles find each other. If the medium was fluid, they turn away from each other. They're crystalline, they find each other. And they find each other in a rather dramatic way. This shows one particle initially pointing in the y direction, the other particle initially pointing in the x direction. The y guy starts walking because it can sense the trail left by the x guy. The x guy senses nothing from the y guy, and so the x guy is able to sneak up on and capture the y guy. So this thing has a kind of stealthy approach and capture. You see this in great detail in the experiments and the simulations. But it really was a prediction of our simple-minded, purely mechanical theory. Purely mechanical, but active forced theory. And just to show it in a particularly dramatic way, Rahul Gupta, my student, created this movie, which, as I said, is a mechanically faithful simulation where an array of particles finds each other and then stays together. I can tell you a lot more, but I think it's best to close here. So I hope I've convinced you that living matter is usefully viewed as active condensed matter. It's a natural language for a condensed matter physicist to describe living materials. Equations written down in total innocence of the actual experiments and on pure thought grounds turn out to lead to successful predictions in cell and tissue and organism groups. We wrote down something from an organism group. It works in the interior of a cell. We also have progress that I didn't talk about on the large-scale stable flocking behavior in fluids when you take inertia into account, a whole bunch of other things. I also showed you that much wisdom can be gained by creating minimal artificial recreations of motility in these simple vibrated systems. And I showed you that a small number of motile particles can create coherent flows among a large number of non-motile ones. And I showed you how in an elastic medium, particles can sense each other in a non-reciprocal way and catch each other. There's all kinds of stuff to do on this subject. And I encourage you to read more about it. So I'll take questions now. Thank you.
Thank you, Sriram. So, questions, if you can raise your hand or something, and then we can. We do have an extended question and answer session at the end for everybody, but if somebody has a question, well, I guess uh, let me start off, and then maybe somebody else can, get into the act. So, yeah. So the what you showed at the end is fascinating. So there's this asymmetry. It's like the follower and the leader, and there's the situation at the front is. It is sort of the non-symmetry of the thing. The situation at the front is completely different from the situation and behind. So that is coming from because the actual medium, I mean, that's just a layered carpet of beads. So, but it's actually coming from that term that introduces the asymmetry. Is that coming from the movement or the shape of the particle?
The point is this: the effect of one particle on the medium is not because it's sitting there and has a shape, but because it's pointy and moving. So it is a moving point force on the medium. So it's a moving point force. That mathematical form that I wrote down is like a wake. It has a disturbance behind and is kind of blunted in front. It's a consequence of simple mechanics, but mechanics of an object moving through a medium. The second part of the story is that if you like, these are two particles. The effect of the particle in the medium is to create a distortion. The effect of the medium on the particle is to reorient its direction of motion. It's rather like chemotaxis. Well, what happens in chemotaxis really is it's not like there is a potential energy that the particle is trying to go down. It's that the thing already has its motility mechanism. Its speed is determined by an internal controller. Its direction of motion is determined by which way it's pointing. And what gradients do ultimately is to reorient the direction of motion, right? Because how can it? And so this is an elastic variant of chemotaxis, actually, in a certain sense. It's not noise-based chemotaxis. There are also active colloids which respond to, if you take a colloidal particle and cover half of it with a catalyst and put it in a medium containing a chemical, the catalyst breaks down, then this object becomes motile. If you create a gradient in the substrate, in the catalyst, then this particle reorients its direction of motion that way. So because the interaction is not coming from a pair potential, the direction in which it moves is set by the gradient of the field that it's sensing, and its speed is determined internally. This funny combination leads to non-symmetric interactions. They don't come from a pair potential at all. So that's the story. And this theme occurs in many places. The work by Saha Golestani and others, and by Yu and Marchetti and others, also has a similar spirit. That is that non-symmetric interactions are generic in active matter, because typically active matter sets its speed not by an external force, but by its own motor. And changes in its momentum are set by only primarily changes in its direction, which are gradient responses. So that's the thing. And this is a realization of that in an elastic medium context. Sorry, I brought too long an answer, but
no. I mean, I think so. Yeah, no. I mean, I think let's. I think the audience can sort of think and ponder it, and hopefully there will be a question. Atta has a question. Atta, go ahead.
Sure.
Sriram, a wonderful talk, I would say. Thank you for this one. Thora, I would like to know the nature of these asymmetric forces which acts in this. Can they be scaled to different scales? Can you describe a renormalization group theory kind of thing for such kind of mechanical mechanisms?
The analysis, you might be able to do it. These forces are not predominantly coming from fluctuations. These are more, I mean, if you wanted to scale, okay, I mean, let me first give you a disclaimer, which is that we have not looked at what happens when you have a large number of such particles. Some effects like screening in electrolytes and so forth, those kinds of effects are likely to be there. They are certainly there in the analogous system that we have studied in more detail, which is active colloids. there, if you have just two particles, suppose, imagine you have the following. Let's not think about rods and elasticity. Let's think about particles with one face of which has a catalyst in a medium containing a reactant which that catalyst likes to break down. Then you know that what can happen, I didn't mention that in this talk, is that the catalyst will make, when it makes contact, I mean, the reactant will make contact with the catalyst will break down. So then on the surface of the particle, you'll have one part which has more reactant and one part which has less reactant, or one part which has more product and one part which has less product. Therefore, along the surface of the particle, there is a solute gradient. When you have a solute gradient, you have osmotic flow. And that osmotic flow makes this particle into a swimmer. But now supposing you have a uniform reactant field and two solute particles in that, two catalytic particles in that medium. They will modify the reactant field in their vicinity. And because the reactant or the product for that matter is diffusing, you will end up getting 1/r interactions between these two particles. Because the diffusing field with a source or a sink in three dimensions will have a 1/r decay. So now these guys will talk to each other at a distance. But if you put in more particles, that decay will be that thing will be modified by something very much like screening in electrolytes. Similarly, when you have polar particles moving through an elastic medium, in 2 dimensions it's a log, in 3 dimensions it's a 1/r. And then if you have many particles, something like screening, which is related to normalization, does take place. These ideas have been explored a little bit, I think, in catalytic particle systems, not yet at all in our kind of system.
So I have a question like, can one apply such kind of theory, for example, like maybe a hypothetical situation of a thin fluid on a reconstructed surface, which somehow can make and break bonds momentarily with the fluid or something like that? I mean,
interesting question.
I'm kind of thinking with the first talk. I mean, the first talk in mind, the Talat's talk, because she was So maybe if one has some reconstruction.
So I think the point is this kind. If the making and breaking is not of the equilibrium kind, but breaks detail balance. Supposing you have a surface, and supposing rather than letting the making and breaking of bonds be at thermal equilibrium, supposing you are forcing it in some way, supposing you're irradiating it or doing something, supposing you're shining light at it. Supposing it's, let us say, a photoactivable liquid crystalline monolayer, and you keep shining the light at it. Or supposing it's a layer of bacterial rhodopsin, and you keep shining light at it. Then those kinds of systems, any of these systems in which the dynamical processes are completely off detail balance, those become always a weird kind, some kind of active matter. Precisely which kind will depend on the spatial symmetries of the structures involved. But you can imagine doing these kinds of theories for those systems in some sense.
Yeah, thanks.
Okay, great. So we should move on. There will be more, as we have a question and answer session, but Ammar, are you ready to go? Because, and then we have a break right after Ammar's talk. So we can eat into the break. So